Hi everyone, Professor Rosenthal here, and in this lesson we will take a look at a topic called Newton's law of cooling. Now in the previous segment we looked at exponential growth and decay and we learned something very interesting, and that is if you simply happen to know that the rate of growth of a quantity, the rate of change of a quantity is proportional to the existing amount. Proportional means a constant times itself. Basically, we can from there determine, so if we have dy over dt equals k times y, we did the work and we found out that the function is actually exponentials. It's c times e to the kt. We did the derivation of this. So there, the only assumption was that the rate of change of the function be proportional to the existing amount, just like the way money grows in a bank. The more you have it, the faster it's going to grow basically, and it's only proportional to how much you have. Same thing with the way diseases spread. The more people have the disease, the faster it's spreading, because the rate of growth, the rate of change of the quantity, whether it's a virus, whether it's a money in the bank, the rate of change is proportional to the number of people who have it, or proportional to the total amount of money that exists invested. So it's proportional to the existing amount. So this simple phenomenon, this simple assumption led to this exponential equation. So again, the amazing thing about calculus is that you can use it to model real life situations. So here we're going to take a look at a different assumption, a different real life situation, and then use that assumption to come up with a mathematical model to represent how quantity cools off. Okay, so here the assumption is going to be as follows. So basically, we're going to look at the rate at which an object is cooling off. And if you think about it, what do you think that might depend on? So if you think about it, it might depend on how hot or how cold the temperature of the object, right? But what else might it depend on? How fast this object cools off. So the current temperature is important, but perhaps even what's more important is where the object is placed, because if it's placed outside, in a snowy environment, very cold, the object is going to cool off very fast, right? On the other hand, if it's just sitting on a hot day in Florida, it's sitting out in a humid weather in 90s, the object is not going to cool off as fast. So it turns out that what really matters is the rate, the temperature difference between the object and its surroundings. That's what truly determines the rate at which an object will cool, how fast it will get colder. So we can actually write that as a simple equation as follows. So assume capital T represents the temperature of an object, and assume capital M represents the temperature of the medium, surrounding medium. So if it's in a snowy environment, this might be like 30 degrees, 28 degrees. If it's a hot Florida day, it might be like 95 degrees. So M is the temperature of the surrounding medium. T is the temperature of the object that is cooling off, and small t will be the time. So here's basically what we just said, written as a one simple equation. So the rate at which the temperature of an object, again, think of this object as a cup of coffee or a lemonade you put in the refrigerator just cooling off. So just think of an object, the rate at which temperature changes, so the rate of change of temperature with respect to time equals, is proportional to the temperature differential between the surrounding medium and the existing temperature of the object. And the way we're going to write that is as follows. So first of all, temperature is decreasing. To represent for that, I put a negative sign. It's proportional, meaning a constant times. It's proportional to what? Proportional to the temperature difference between the object and the surrounding medium. And typically the object happens to be have a higher temperature than the medium. So that's why we put T minus M. So this quantity will be positive. Um, K will be positive, and the negative here makes the whole quantity being negative. So the rate of change of temperature is negative, meaning as it's cooling off, the temperature maybe is going from, let's say, 100 degrees to 75 degrees, right? So it's decreasing. Therefore, it's going to end up being a negative quantity. So the simple equation will lead to uh, a description of the function t the temperature function in terms of time. So we're going to be able to, so once we get what this function is, we're going to be able to determine at any given time t what the temperature of the object is from just a few basic things that will be given to us in a problem. Now, just like in the exponential growth and decay, we had a simple equation and that led to our solution. So our simple equation there was dy over dt equals k times y. And from there we got y equals a constant times e to the kt. So this was actually called a differential equation, a very, very simple differential equation. So here we have a similar situation. So let's solve it. Let's solve it for the temperature function capital T of t. So to be able to solve an equation like this, first step is, this is called a separable equation. So you want to put similar quantities on the same side. So capital T is one of the variables, and lowercase letter t, the time, is another variable. So put the capital T's on the same side and lowercase t's on the other side. So to be able to do that, I'm going to divide both sides by capital T minus m, while at the same time multiplying both sides by dt. Okay, so that will lead to, so first step, I guess I did in two steps here. First, multiply by dt, and then divide by t minus m, both sides. So here's what we have. So I divided this side by t minus m. So here they cancel, and divide this side by t minus m. Okay, so we have two variables. Capital T is the temperature, lower t is the time, and we separated them. Capital T is on one side, lower t is on the other side. Notice you see the dt. To get rid of a dt, a derivative, we're going to apply integration to both sides, integrate both sides. So that's what I have. So now here we're integrating this quantity, and the only variable is capital T on this side. Okay, so think of m as a constant. So you could do a little u substitution if you like, but this is going to require for the natural log function, as you may recognize. So the integral of this will be natural log of t minus m, ln of t minus m. And I don't use the absolute value here because I know t minus m will always be positive. On the other hand, what is the integral of a constant with respect to time? Think of it as 5 dt. The integral would be 5 times t, right? So that's what I'll have here. So negative k times t, and don't forget to put the plus c, the constant for integration. So now remember, my goal is to determine what is the temperature function in terms of time at any given time. What's the temperature? So I need to solve for t in this equation. And to do that, I need to get rid of the natural log. So you may remember this trick from the exponential growth and decay section. I'm going to exponentiate everything. I'm going to say e to this side equals to e to that side. Okay. So let's exponentiate both sides. So e to the left side equals e to the right hand side, and e to the ln, they will cancel each other. So at this point, what we're going to have is capital T minus m on the left-hand side equals e to the negative kt plus c on the other side. So at this point, notice that I can write this quantity as e to the negative kt times e to the c. If you have any doubts about this, think about going backwards. If you were to multiply these two quantities, you would be adding the exponents, right? Because the bases are the same, and you will be getting e to the negative kt plus c. We applied this trick on the last section with exponential growth and decay, if you may recall. And then e to the c is yet another constant, which I'm going to call that, let's say, capital C. So at this point, I have t minus m equals capital C times e to the negative kt. And remember, I'm trying to solve for capital T, the temperature at any given time. So capital T equals, add m to both sides, m plus c times e to the negative kt. So this is an equation that we obtain from some basic assumptions. So we're going to be able to model the way an object cools off, and the way we got this equation was by using calculus. So we're able to model a real life phenomenon using calculus. And in this case, the real life phenomenon is how the object actually cools off. And believe it or not, one of the examples you will be able to solve at the end of this section is you'll be able to solve a murder mystery. Let's say an object was found, and a body was found in a room, and you know it has cooled off certain to a certain point. You know how many minutes has passed, and with a few more information, you'll be able to determine the time of death based on how fast the cooling has occurred and based on the surrounding temperature. All right, so before we get to that example, let's just do something a little bit simpler.